Let's look at an application of derivatives called particle movement problems, or one-dimensional movement, sometimes we call it that. So, but first let's get a background here, all right? We know that the derivative can be interpreted as a couple things. One, it's the slope of the tangent line. That's a key concept there. And we also have seen that the derivative is the instantaneous rate of change of a point. You can think of on a graph or instantaneous rate of change of something that's moving. And so let's think of the physics kind of side of things here when we have moving stuff, moving objects. So we're going to start with a function. We'll call it s of t, and that will be our position function. That'll tell us an object's position. And if that's its position function, then if we want to know the change in position, we call that velocity. So change in position is velocity. So the object, since it's the change, and change is a derivative, the object's velocity can be found by taking the derivative of position. So velocity is a derivative of position. Now, if we want to change in velocity, we call that acceleration. So acceleration is a change in velocity. Oops. So we have acceleration is the derivative of the velocity. Okay, so acceleration is the derivative of the velocity. And so we have this very important relationship here. If the position is s of t, sometimes we'll call that different things, but let's just call it s of t for now. The velocity is the derivative of that, and acceleration is the derivative of velocity, which is also the derivative of position. So in other words, acceleration is the second derivative. Okay, so we have this kind of hierarchy. If we want to find acceleration, that comes from the derivative of the derivative of the position. All right. So let's try this out. Let's answer some questions about this. Here we've got a diver who's diving off of a diving board. All right. So here's a function that represents the diver's height at time 0. He's at 32 feet high. So if you plug in 0 here, you'll see that the position is 32, because that's where the platform is. And we want to figure out what his velocity is and some other things. All right, so this is measured. Units are important here. So notice that t is measured in seconds, and the height is in feet there, right? So what's the diver's initial velocity? Well, remember, velocity is the derivative of position. So we've got to say, well, we're looking for initial velocity. We're looking for v of 0. So we've got to find v of t first. V of t is the derivative of s. And looking at the function up above, using our power rule, we have s of t equals negative 32t plus 16. Okay, and so the velocity at time 0 is negative 32 times 0 plus 16, which is 16. So 16, in this case, we're going up. So that's 16 feet per second. So that would be how quickly that diver pushed off the diving platform there. So what's the maximum height of the diver? Well, where do we find the maximum height? Remember, the maximum height is when the velocity will equal 0. So when velocity is 0, we have a maximum. Or just think about if this was a curve, which it is, a parabola, then we can find the extrema when the derivative of s is 0. Well, the derivative of s is velocity. So our velocity was negative 32t plus 16, and we want that to be equal to 0. So we got negative 32t equals negative 16. So t equals, divided by negative 32 on both sides, and we get a half. So t is 1/2 second. So at 1/2 second, velocity will be 0. Well, when does the diver hit the water? Well, the water is a 0 height, so that position will be 0. So that's a position thing. So we want S of t to be 0, a height of 0. So S of t is our function, our original function here. So that's just our negative 16t squared plus 16t plus 32. I'll make that equal to 0. And if we go ahead and divide everything by 16 here, negative 16, how about that? We're going to get t squared equals, minus t minus 2 equals 0. And if we factor that, we get t minus 2 times t plus 1, right? So the times are, here we got 2 seconds and negative 1 seconds. Well, we don't want negative time here, so the answer we're going for, t equals 2 seconds. That's when the diver will hit the ground. All right? Well, what's the velocity at that 2 seconds? Well, velocity is our v of t, or in this case, v of 2. So we found out when he hits the ground, so what's the velocity there? Well, let's use our velocity function that we have up here, negative 32t plus 16. So we have negative 32 times 2 plus 16. And so that's going to be negative 64 plus 16, which is negative 48 feet per second. What does the negative mean here? Well, a positive direction in this case is going up, and a negative direction is going down. So positive direction to start, and then negative direction going down, because we're losing altitude. So let's talk acceleration now. So acceleration means that we have a change in velocity. So we're going to need the acceleration at 1/2. And also we're going to need a of 1. So what's the acceleration at 1/2 second and 1 second? Well, a of t is the derivative of velocity. It is the change of velocity. So the change of velocity is, with our velocity function here, negative 32t plus 16. So we've got the derivative d dt of negative 32t plus 16, and that is just negative 32. So the acceleration is negative 32, and at 1, negative 32, because that's the acceleration due to gravity. Negative 32, the units here are feet per second per second. Or we say feet per second squared, all right? So that's feet, that's how many feet per second per second. Okay, there's another way we say it. Feet per second is acceleration. All right. So that's the idea of an object flying through the air and how we can find those. Now, let's switch gears to a point on a number line now.